All right. Well, you made it to the end. Congratulations. Um, we lost a lot of people this quarter in this course, which is pretty unusual. Sometimes I might have one person drop along the way. Well, we started with like over 20 people in here, and I think we've lost like a third of the class. Say again?
Like, are you saying not many people actually dropped out of the class, or just aren't in Zooms?
No, we actually had about a third of the class drop during the term.
Wow. Really? Wow.
Yeah.
Really? Why is that so?
It's a good question. I mean, this course is so much work, and I think everyone's still trying to kind of adjust to the online thing. We'll get good at online just about the time we're going back in person, but I think it's just got its own challenges, and some of the people who have talked to me, there's just other things coming up. 250 is a course that you can take twice a year, and it's a prereq for a couple of classes, but it's somewhat flexible time-wise, and so it just seemed like alignment of planets. I don't know. A lot of people, this just wasn't the best quarter for them to be taking it. And yeah, we'll be back in person soon. So my classes will start having in-person offerings in winter. That's the current plan. Fall is still going to be online, so if you're starting the 200 level CS sequence, we'll start off online in fall, but then beginning in winter, we'll have one class in person, one class online, all things being equal. So that'll be good, because we can just do a lot more when we're actually in a physical classroom. This class, usually a lot of the class time is spent with students working at the board, in groups of 2 or 3 students, working out problems while I go around and see what people are doing, answer questions, ask them questions, and so on. And it's just a lot more interactive. And this is just a lot of materials you just kind of try to take in through a lecture. It gets overwhelming pretty quickly. So having made it through to the end, congratulations on that. It's a course that whatever you get out of it is going to help you, and as long as you got enough out of it to move on, that's all good. But it's stuff that will come up, particularly if you're computer science. When we get into discrete structures, when we get into some data structures classes, you'll be flashing back to this course a lot. It'll be like, oh yeah, we did this in 250. Oh yeah, this is just De Morgan's theorem again, that kind of thing. So it's all pretty good stuff. All right, so I've got most of your labs and homeworks graded, with comments put in. Let me just talk about that last experiment in lab 7, the event detector, the 5 out of 16. Just because that's kind of one of the quirkier experiments. The goal was to you have a clock. We always have clocks with our circuits, and you have some input. And the input, it might be high, it might be low, it might do all kinds of things. And if we think of this as, a positive edge triggered system, then every time that the clock ticks, and if it's positive edge triggered, a tick means when the clock changes from 0 to 1, we want to look at the input. And we want to remember what value we saw. We saw a 0, a 0, a 1, a 1, a 0, a 1, a 1, and so on. And continually, every clock tick, we want to look back at the last 16 numbers that we remembered, and we want to see if exactly 5 of them were 1. So assuming that we had a bunch of zeros in the beginning, right, at this point I've seen 4 1s. If I had another clock tick over here, then right here I would see another 1. At this point I'd say, oh, I've seen 5 1s in my previous 16 inputs, and so at that point my output would go high. to say, hey, as of this clock tick, this rising edge of the clock, if I look back 16 numbers that I remembered, 5 of them were 1. And so it's not a system that, you know, ticks 16 times and then you calculate an output. You calculate the output every clock tick. And so you need to constantly be looking back at the last 16 samples and seeing if 5 of them were asserted. And so we can do that with, you know, an always block. And Verilog, you know, if it's a positive edge device, we just say at the positive edge of the clock. If we wanted a negative edged clock, we just say, you know, at the negative edge of the clock. So what we can do is we can have a register, which I'll just call memory, right? And I'll say memory 0 is assigned whatever the input is. Memory 1 gets a copy of whatever was in memory 0. Memory 2 gets a copy of whatever was in memory 1, and so on. 16 bits, so memory 15 is the last bit, gets a copy of memory 14. So that's our shift register. And the input feeds that first bit, and the first bit that was what was in the first bit feeds the second, and so on. So in hardware, we have 16 D flip-flops. We can think of them like this. And our input is going to go into memory 0, and each of these is going to feed the next. And they're all clocked together. All right, so that's a possible hardware implementation of what we've got here so far, without the bug. And it's useful when you're doing Verilog to be thinking about what the circuitry is, right? This is that first hint that I gave you was don't think of it as code. If we think of this as, you know, C, and we think of this as a bunch of assignment statements, we can get off track. Think of it as hardware, right? We're not going to design the hardware using hardware and flip-flops and things like that, but you want to be thinking when you're writing these statements that you're putting down hardware and connecting it together. So here's a shift register, right? The input goes into this stage, the output of that stage, mem0, goes into mem1, and since these are non-blocking assignments, they all happen simultaneously, which means the clock fires all 16 flip-flops clocks, and simultaneously whatever was at the input gets loaded into this stage, this D flip-flop. And so now we need to build a circuit which looks at these 16 outputs, mem bracket 0, mem bracket 1, up through mem bracket 15, and says, are exactly 5 of these equal to 1? And we can do that a variety of ways. We can write, you know, 65,000 if statements to say, you know, if this is a 1, 1, 1, 1, 1, and these are all zeros, then yeah, we're good. If this is a 0, 1, 1, 1, 1, 1, and all zeros, we're good. If this is a 1, 0, 1, 0, 1, 0, 1, 0, 1, and then 7 more zeros, we're good. Right? But there's lots of combinations. So really easy way to do this is just add all those bits together. We've got 16 bits. Say again?
Sounds like someone just straight up fell off their chair.
Oh, hopefully not. 16 bits, and some are zeros, some are ones. If we add those bits together, we will get a number between 0 and 16. And that number will be the number of bits that were equal to 1. So now we just have to add these 16 bits together. And there's a couple of ways to do this. We could say if the sum of all of these is equal to 5, set your output to 1, else set your output to 0. So this is assuming that output is a flip-flop, because we're using these non-blocking assignment statements inside an always block. So if this is a register declaration in Verilog, this will, basically synthesize as a flip-flop. This would set the flip-flop value equal to 1 or 0 based on this sum. But there's one small problem with that. Anybody happen to have done exactly this and seen something odd in their simulation? It's very, very particular.
It doesn't reset back?
It should reset back, actually.
I got a bunch of unknowns at the beginning, but I think that's normal.
So unknowns in the beginning are normal, because until, we've had a few clocks, this is getting its value from M1, which is undefined to begin with, until it gets a value from here, from in. So that's also normal. There's a really subtle issue.
If you set them all to 0, if you set all the beginning outputs to 0 as a base, then none of them will ever be undefined.
Right, so if you initialize everything to 0, which you can do in Verilog, which may or may not synthesize, or you could have a reset input that would say, if reset is 1, set all of these to 0, then you can avoid those unknown conditions in the startup. Good. Anything else?
Will that out won't work.
Why is that?
Because M0 may or may not be a 0 or a 1 at that point. Unless the if statement will only run after everything else above it is done.
Yeah, so you're homing in on what I was looking for. Remember, everything inside your always block happens in parallel. As long as you're using these non-blocking assignments, all of these things happen at the same time. The universe is parallel, right? As far as we can tell, hardware is parallel. And that's another way in which we need to not think of this as code. So while these things are happening, in other words, while these things are shifting through our flip-flops, this statement is also going to execute. Which means this is going to happen, this assignment of the output is going to happen before the inputs have gotten loaded into the flip-flops. This is going to be based on the values of your previous 16 bits before the current clock tick. And so this circuit's always going to lag 1 clock tick behind. And if you're really down looking at the simulations, you'll notice that. You'll set your input to 1, and you'll look at your flip-flops, and you'll have 5 ones stored in there, but the output stays low until the next clock tick. Right? Because this is a flip-flop that's being loaded based on this sum at the moment of the clock tick. In other words, here's our...
You mentioned that, I did notice that.
Okay, cool.
If you set it just to a regular equal sign, it works.
Yeah, so like this, you get a lag, right? Because the check to see if the sum is 5 is happening on these saved values. So there's some ways around it. If you use blocking assignments, then this will happen after these have taken place, right? And you get this more kind of what we would think of in procedural code, where first we shift these things in, and then we add them together, and we check to see if they're equal to 5. If you make all of these non-blocking, you got to be really careful on the order of this. If I do these in a different order, my input will race all the way through all 16 stages at once. With non-blocking assignments, I can put these in any order that I want, and it'll work fine. The other way to do this is with an assignment statement, like this. So an assignment statement, this would be outside of my always block, and this is not something that's triggered in response to a clock tick. This is building a wire. So it's taking the contents of these registers, it's adding them together, it's checking to see if it's equal to 5, and then it's sending that straight to my output without loading it into a register that's clocked. And so once the clock ticks, it will take, a brief instant of time, an epsilon, for everything to shift through. But at that point, this add circuit will add those new values, right, post clock tick, and if they're equal to 5, it'll set the output to 1, otherwise 0, and so that'll get rid of the lag also. And these are all just kind of nuances, right, that you develop, by working more and more with Verilog and debugging circuits and so on and so forth. And it's part of, where this is so different from writing code. But, just like you get really good at writing code and using a debugger to find bugs, and you learn, tricks so you can think about index 0 and fence post problems and things like that, you get the same way with hardware. If this is what you do every day and you get your 10,000 hours of Verilog coding, this becomes second nature. But it's super mysterious when you're first starting off. It's still pretty super mysterious to me. I do not have a lot of Verilog experience, but every time I jump into it, I learn a lot more stuff. So any last questions or thoughts on all of that Chapter 7 stuff, Verilog, the last lab, and so on? All right, well, that brings us up to just kind of reviewing the course and talking about the final exam. Let me talk about the final exam first, and then we can review material. So final exam is on Tuesday, 12 o'clock. Okay, so it's the regular Clark exam schedule. It will be much like the midterm. It will be an assignment that appears on Canvas and opens up at 12 o'clock, noon. And you download it, read the problems, write up solutions, upload those solutions as a PDF. And you have to take it starting at 12 o'clock. It's not open all day. It's open at 12. And it's due, unless you have extended time arrangements, it's due at 1:50. I will try to make it relatively shorter than the midterm, right? So it may be longer than the midterm, but not twice as long as the midterm. So the midterm was pretty tight on time, and you have twice as much time for the final. So I'll try to make it less than twice as much material to line that up. But you can expect the problems are going to take a while, right? So you've been doing the homework. You know how long it takes to analyze a state machine or to synthesize a state machine. These are long problems. So I strongly recommend have a good way to get a clean picture of paper and do your work on paper. Trying to do K-maps, trying to do state tables, state diagrams on a computer, generally not very efficient, right? Much better just work on paper, have some good sharp pencils available, nice eraser, and so on. Get yourself in your optimal environment that you would use for doing homework, for example, and work these things out. Get clean pictures of them. Put them into a Word document, a Google Doc, something as you're working, so that you don't have to try to assemble your document from a bunch of images in the last 5 minutes or something. And generally, material-wise, it's going to emphasize the second half of the course's material more than the first. But, everything we did in the second half used the stuff that we learned in the first half. So you can't forget K-maps just because they were in the first half of the course. Because you need to use K-maps to do state machine synthesis, right? So more of the questions will look like, the homework questions from the second half of the course. But that just uses the stuff from the first half more. So main topics would be, we'll go through a detailed list in a minute, but the main new topics are basically, state machines, and to some degree Verilog. I might have one Verilog question, okay, probably like 10 points, so it's not a make or break, because I know Verilog is different. But mostly it's going to be state machines, flip-flops, circuits with clocks, things related to clocked circuits, timing diagrams, things like that. Um, so any questions about logistics, that kind of thing?
So you said we had to take pictures and put them in a Word document. Is it different than like the previous exam? We just wrote it all out on paper and then took pictures and.
That's fine, yeah. You need to upload a PDF. That's the only requirement, right? You need to upload a legible PDF. But in homeworks, I've had people who have consistently typed up their homework using a text editor. And if you want to make a state transition table, it's got 14 columns going across. And if you spend the time, you can do that with a text editor and make it look really nice. But on an hour and 50-minute exam, that may not be the best way to use your time. So I'm suggesting if you're worried about how long it takes to type these things up, don't type them. Just write them out by hand and turn those into images. Scan them, take a picture, or something. But whatever works for you is fine, as long as I get a PDF file that has all of your questions in order. All your answers in order, that's what I'll grade.
Cool, thanks.
Yeah, you're welcome. All right, well let's just go through a list of topics. So let me bring up Canvas. I posted this list the other day, yesterday I think. So not necessarily all inclusive, and not everything you see on here will appear on the exam, but just kind of a review of some of the stuff we've done. Let's see, scanning, taking photos, and submitting that way takes me 10 plus minutes because of slow internet and devices. That's a drag. 10 minutes is a long time to upload. So one idea would be, partway through, like maybe, 30 minutes from the end, go ahead and start your upload at that point. And then while it's uploading, you can spend that time working on the last problems, and then just upload the new stuff. And if you upload, two files, and the first file has most of the questions, and the second file has the remaining questions, right? I'll just grade those two as one exam, and so that can help, perhaps. But don't try to figure out how to do that during the exam, right? If you want to do something like that, practice ahead of time. Figure out what makes sense, so that you can spend your time doing digital logic. All right, and general guideline, right? Look at your homeworks, look at your labs. Those are good representations of the kinds of questions that I'll be asking you.
There are a lot on flip flops, like they're specifics like T flip flops, K flip flops, SRs, etc.
Probably, yeah, and it may not be, a 50-part question of, here's this flip-flop, here's that flip-flop, but, if you want to analyze or build state machines, you got to understand the flip-flops that they're made from. So they'll definitely come up like that. If I ask you to draw a timing diagram for a circuit, you got to understand how the flip-flops work to be able to do that. So yeah, at least indirectly they'll come up. But I probably won't, just show you a flip-flop and say, write the table for this. But you wanna be able to do that so you can use that information for other problems.
Is this open note?
Say again. Oh, yeah. So you can use any of your notes. You can use any of your old labs, any of your old homeworks. You can use the textbook. You cannot use online sources. Okay, so no Google, Wikipedia, things like that. But any of the stuff that you've used for this course is fair game. Um, I'm gonna mention Chegg one more time. So I know I talk about this a lot, but I had multiple homework sevens and multiple lab sevens with Verilog code that was verbatim what you can find on Chegg, and it's a really steep, slippery slope, right? So some of these cases I'm still deciding what to do with the homework, um, but in general, I'm assuming that this was inadvertent, and that the goal wasn't actually to take credit for somebody else's work, but that somebody was stuck and looked at some online stuff like Chegg to try to get some ideas, and then when they wrote the code, it ended up looking exactly like what they had seen, because you can't forget things that you see. But that's a huge, huge, huge issue on the final. That will be an F in the course if it happens on the exam, and it will be an F in a course probably in the future if it's one of my courses. So really, really be careful of that, right? And on the final, right, you're not supposed to use any online resources. Even if you're just looking to remember, something that you forgot to put in your notes, you're not allowed to do that, right? Just your own notes, which includes your homeworks and your labs and the textbook. That's pretty much it. So stay far away from Google searching for those 2 hours. But before then, you can look at anything that you want online, obviously, and you can make your own notes that include anything that you think should be in there. But your best bet is, try to make a set of notes that are meaningful to you as you go through and you rework homework problems or work some of the problems that you find in the textbook and so on. Be making notes for yourself about what you have to do, and then go through and condense those down to a small set of pages. That's how you do school, right? So that's good preparation. All right, let's see. We got a lot of time here, but you probably don't want to listen to me talk for 80 more minutes. Um, so let's start from the end and go back to the beginning, because the earlier stuff probably doesn't need a lot of comment because we've been using it. So let's start with the latest stuff.
A lot for just one exam.
Say again.
This is a lot of review just for one exam. I'm like,
Well,
I'm
this
supposed to get that in for 2 hours.
this is the review of the whole course, right? But like I said, you're not going to get a question on each of these things because that would be a ridiculously long exam. Um, but this is why this course is so challenging, because it's all this material and it just compounds. But particularly this earlier stuff up through sequential and combinational circuits. Most of this earlier stuff you really don't need to do a lot of review on, right? I mean, how many times have you made a schematic diagram in the past 10 weeks that involved a switch, right? And unless you've been losing points on your switches, you probably know how to wire up a switch with a 1K pull-up resistor and so on and so forth. You know what an AND gate is, right? You probably don't need to review that. So I'm trying to list the topics in here, but this isn't necessarily stuff that you're going to need to spend an hour on each of these topics. But yeah, it does look kind of intimidating lengthwise.
Do we have to draw the schematics, like the internal schematics for something like a D flip-flop or a T flip-flop or JK?
No, I won't do that to you.
Thank you.
Yeah. We did that in the beginning. We sketched out a set reset latch using a pair of cross coupled NOR gates, and that's a nice thing to know. But I won't ask you to do that. When we deal with flip flops, we'll start with the flip flop as a device with a D input or a JK pair of inputs or something, and build up from there. So let's talk about Verilog, and there's more detail at the end because it's new stuff since the midterm. But Verilog, what would I like you to know? Basic concepts of a hardware definition language and the notion that this is different from programming language. In particular, an HDL is describing a piece of hardware. A program is describing a set of steps, an algorithm, right? So just being aware of that difference. The module statement, which is how we start, defining a hardware module. So module in the name of the module, parentheses, lists of inputs and outputs. And just get a piece of Verilog code that works for you in the LDEC simulation for a combinational circuit. Put that in your notes. Write a piece of Verilog code that uses an always block with a clock that works. Put that in your notes. And those are probably good templates for most of what you'd encounter on the test. So the module statement, the idea of using an assignment statement for combinational circuitry. So if you want this to be equal to some logical combination of these variables, we use the assign keyword. So assign output equals and then the algebraic logical expression on the right. Know how to use the ternary operator just because it's really useful if you want to conditionally assign your output based on some input or some condition instead of doing an if then else, which is hard to do with an assign statement. We can use this ternary operator. So know how to do that. And then if you have sequential circuit with a clock, we're going to use an always block, so always at, and we usually put in here either positive edge or negative edge followed by the name of our clock signal. And then inside there we can put in whatever assignment statements we want. And so we use this less than equal to do a non-blocking assignment, and that's the only assignment we need to do. And inside that always block you can do if then else, because we're going to assign a value by loading it into a flip-flop, right? So it's only going to make that assignment when this always block fires. So typically on the edge of a clock, and so we can put some logic inside there, and that's enough for pretty much all of the Verilog that we've done, and anything I might ask you on the exam. All right, so finite state machines. These are, a set of memory, a bunch of combinational logic, a feedback path, and a clock. Right, that's your basic state machine. And the clock ticks based on the inputs to the memories take on new values. And then the outputs of the memory feed that combinational logic. It processes those outputs along with inputs to the system, and it generates new inputs for the flip-flop that wrap back around, go back in. That's your feedback path. And it can also generate outputs from the system. So it's a very general model for a system that's clocked and moves from one state to another based on its current state and its inputs. So that's the basic setup. We talked about maximum clock frequency. So if this is your memory and this is your combinational logic, once the clock ticks, the outputs take on their new value. They go into this combinational logic. There's some propagation delay. So we can't tick the clock until this propagation delay has passed, which means these outputs have taken on valid settings. And then once those inputs go into the inputs of the flip-flops, we have to leave them stable for whatever the setup time of the flip-flops is. So tau SU. And so if we add the propagation delay of the combinational logic and the setup time for the flip-flops, that's the sort of minimum clock period, right? We can't tick the clock again until that much time has passed. If we do, either this won't be outputting the correct values, or those values won't have been sitting here long enough to satisfy the setup time. So we can calculate the maximum clock frequency based on the minimum period, which is the sum of those propagation delays. So we saw some homework questions with that. That's what this maximum clock frequency is about. So state diagrams, well, state machines in general, right? Like I said, present state, input, output, next state. So we can draw this as a diagram. Right, whatever. And so we might have, you know, a given state and an input value. And if you had a 1-bit input value, you can just specify that 1 bit. If you had, you know, multiple bits like x1, x0, this might be a pair of bits. So this would be 0, 0, 0, 1. Maybe this is 1, 1, and this is 1, 0, and this is 1, 1, and so on. And in here we put the name of each state, and the names are basically arbitrary. And if we have mealy outputs, so outputs that potentially change based on the inputs, we can list those after the slash. So maybe there's one mealy output, we'll just call it Z0. And so we could, you know, specify what that value is. And so on. And if there's more outputs, those depend only on the state. And so we don't need to list, you know, the more output for this state here and here and here. It only depends on the state, so we just list it inside this state bubble. And so if we had, you know, some Z1 that was a more output, we could list that inside the state. And so we might have, you know, state 0 and state 1 and state 2, state 3, state 4, and we could list, you know, what those outputs were, and so on. And the way you interpret a diagram like this is present state, input, causes an output and a transition to a new state. So it's basically present state, input, next state. And then the outputs, you know, if they're merely outputs, they are generated based on the input. If they're more outputs, they're just based on the state. So mostly present state, input, that describes your current situation, and then when the clock ticks based on that situation, you go to some new state. And so we can do that in a diagram, but we typically do that in a table. And this is where you get into those really wide tables where you have a present state, input, output, and next state. Now if you have flip-flops which you're using to store your state, then your present state is basically the combination of the flip-flop values. So it might be Q1, Q0. And then the next state will be, you know, the new values of Q1, Q0. So sometimes we write Q0 plus Q1 plus or something like that. And it's useful to have a name. Otherwise we have to call this state Q1 equals 0, Q2 equals 0, Q0 equals 1, right? So we have a name like S0, S1, S2. So there's this state assignment table you make in the very beginning, which says, you know, here's the values of my flip-flops. Here's what I'm going to call that state. So this is state A, B, C, D, or S0, 0, S0, 1, etc. All right, is all that familiar somewhat? It was a while ago, but not that long ago. So two main tasks, and you'll definitely be doing both of these on the exam: analysis and synthesis. So analysis of a finite state machine, you'll have a circuit diagram. It'll have some flip-flops, it'll have a bunch of wires and gates, and the goal is ultimately draw a circuit diagram corresponding to that. And so to do that, you decide how many states you have, and based on the number of flip-flops, it's 2 to that number. You make a state assignment table, and then you start filling out this present state, next state table. Well, how do you do that? Well, if we can list all the combinations of present state and input. That's just an exhaustive list. That's the left side of a big truth table. But if we know this is the present state, and we know that these are the inputs, how do we know what the next state's going to be? Well, we don't unless we know what the inputs to these flip-flops are. So we would add columns. If these are JK flip-flops, we would have J1, K1, J0, K0. And how do we know how to fill those in? Well, we need equations. Where do the equations come from? They come from looking at the circuit. Right? So this is this multi-step process that we went through where you look at your circuit diagram, you write equations for the flip-flop inputs, you write equations for the outputs, and then you fill in this truth table with, the output values, the flip-flop input values, and then based on the flip-flop input values and the current flip-flop state, you can figure out what the new flip-flop state is. So if it's a T flip-flop and T is 1, its output is going to toggle. If it's a T flip-flop and T is 0, its output is not going to change. And so from that knowledge of flip-flops, you can fill in this next state information, and then you know how your machine moves from a present state and an input to a new state, and then you can use that to draw your diagram. So that's the analysis part. The synthesis part runs in the other direction. You start with a diagram. You go from the diagram to a state transition table. And here we're specifying the next state and the outputs based on what the diagram tells us. So this is the exhaustive combination of present state and input, left side of the truth table. The output and the next states come from the diagram. We just copy that information in. But now we're tasked with building a circuit that will cause these behaviors from present state input to next state. So how do we do that? Well, if we want the next state of Q0 to be a 0, and it's currently a 0, and it's a toggle flip-flop, then we need the T input to be 0 in that case. But if we want the next state to be 0 and the present state is a 1, then we need the T input to be a 1 in that case. If it's a D flip-flop, we do something else. If it's a JK flip-flop, we do something else. But by using that knowledge of flip-flops and how we want our current values to change into new values, we can fill in columns for the inputs to the flip-flops, JK, D, or T. And then we ignore all of this. We've basically got, present state inputs. What do we want J0 to be? What do we want K1 to be? What do we want T2 to be? And so on. And now you're back to a first half of the course problem, which says, let's write equations to describe each of these outputs in terms of the inputs. So you do a sum of product or a product of sums, you do a K-map, you minimize, you simplify, and you come up with equations, and then from those equations you can sketch a circuit, and that's your end product of the synthesis process. So those two items are a big chunk of what your exam will be, right? But you've got to understand state diagrams and state machines and flip-flops and K-maps and truth tables and all that other stuff. But definitely analysis, synthesis. So those two big homeworks that we did, I think they were homeworks 5 and 6. Definitely review those. All right. Moving backwards, synchronous versus asynchronous logic. And this was really just introducing the idea of a clock into our circuits. So when we had cross-coupled NOR gates that we used to build an SR latch and then a D latch and so on, that let us store memory, but kind of instantaneously. As soon as you hit the set input, you store it a 1. As soon as you hit the reset input, you store it a 0. And it's difficult to coordinate lots of circuitry that's doing lots of different calculations if they're all just kind of going at their own pace, right? So here's something that's just calculating the inverse of a number. That happens really quickly. Here's something that's multiplying two numbers together. That takes a really long time, right? So this answer is ready long before this answer, and maybe this is going into some piece of circuitry that combines this inverted number with this product, right? And it needs to know that this product is still being calculated. So we introduce a clock usually in digital logic, and we make our circuit synchronous, right? Synchronized with a clock. And that's why, when we build a state machine, all of our flip-flops have a clock input. Those clocks get fed together. All right, so that's synchronous versus asynchronous. We didn't really do anything with asynchronous logic. It's its own thing. So flip-flops. So I want you to understand D, JK, and T flip-flops. I will not ask you about SR flip-flops because they always have that weird fourth state, and they're just kind of a subset of JKs. So definitely D, JK, and T. All right, so know those absolutely. What happens when the clock ticks? They can be positive edge triggered or negative edge triggered, which is basically which direction of clock change causes this thing to do whatever it's going to do. Setup and hold time. So setup time is how long inputs need to be stable before you tick. Hold time is how long inputs need to be stable after you tick. Right? You can't startle a flip-flop. If you're about to tick the clock, your inputs have to be stationary. Tick the clock, they have to stay stationary for a little while afterwards, and then you can go ahead and change them. So that required stationary time before and after, that's the setup and hold time. Flip-flops sometimes have preset or clear inputs. You saw this in the lab where you were building your delay circuit with D flip-flops. So sometimes there's an input that will force the output to go to a 1 or a 0. That's a preset or a clear. And those can be synchronous or asynchronous. If they're synchronous, they only take effect when the clock ticks. If they're asynchronous, they take effect immediately. And your data sheet tells you, which style they are. And they can be active high or active low. So knowing that this input will force the output to be 1, what value on the input makes that happen? Is it a 1 or is it a 0? Got to look in the data sheet, right? So if they're active high, then a 1 on the clear input would cause the flip-flop to clear. If they're active low, then a 0 on the clear input causes it to clear. So you put that all together, you've got types of flip-flops, you've got synchronous or asynchronous presets and clears, you've got positive edge triggered, negative edge triggered. Your packages can have 1 or 2 or 8 flip-flops inside, depending on the device and so on. And so flip-flops are edge triggered, right? They do their thing when the clock is changed, either from low to high or high to low, depending on the device. Level triggered devices, which is what we first started with, which was a D latch, they do their thing when the clock is at a high level or at a low level. Okay, edge triggered do their thing when the clock changes from one level to another. So it's the edge of the waveform versus the level, high versus low. And edge triggered devices we motivated by looking at shift registers. And the idea was if we made a series of latches with inputs feeding outputs, and maybe a load signal. If these are level triggered, the logic is if this input is high, copy the input into this device and send it to the output. And so if we raise the load line, as soon as this line goes high, this input will go into this latch, and it will drive this output, which will go into this latch, which will drive this output and go into this latch and go into this latch. And this input value gets loaded into all of these latches. Unless we were to, like, drop this load line really quickly so that the input had enough time to get into here but not into here, right? So that's a level triggered device. And that's usually not what we want. So instead we have these clocks, and this little triangle on the input tells you it's edge triggered. And so we usually call it a clock line. And now that loading of the flip-flops only happens at this instant. So this is going to load whatever it sees right here. This is going to load whatever it sees right here, and so on. And you don't get things racing through. So you can't make a shift register easily with level triggered devices, but if they're edge triggered, it works really well. And this was your delay circuit that you used in a couple of labs, or a couple of experiments, where you just took D flip-flops and wired them together like this. All right, let's do a 5-minute break, and then we'll come back to this. Well, let's stretch our brains for 5 minutes. All right. More topics. Edge trigger delatch. Timing diagrams. So know how to do a timing diagram. Know how to analyze a timing diagram. Right. You've been looking at them in your Verilog code, and hopefully using the timing diagrams from LDEC to validate your code. So you should be getting better at reading timing, but
All deck on the final.
no, I won't ask you any questions about LDEC, about using it or setting it up or anything like that. So, was that your question? Was I going to ask about LDEC?
I was thinking that if we had a Verilog problem, we would have to do it, test it, simulate it, to have a snippet of the waveform.
No, and if I ask you Verilog questions, it's probably going to be faster not to try to use them, not to try to work with them in LDEC, but just to write the code. All right. Yeah, I guess I should specify whether you're allowed to use LDEC. If I ask you to write Verilog code and you want to use LDEC to like test your code, you can do that. But if I'm not planning on asking you something, you know, harder than what you've already seen in homework, and probably, you know, more along the less difficult problems that you encountered in homework or lab. So probably not worth spending time trying to fire up LDEC, but I'm not going to say you can't do that. So timing diagrams, make sure you understand how delays and glitches are related, and that you're able to, for example, make or analyze a timing diagram related to propagation delays. So we did an example of this where we had, say, you know, an XOR gate with an input A, and then maybe A goes through an inverter back in, and so our, if we call this, you know, Y, and call our output X, our input is either a 0 or a 1, which means Y is the opposite of it, and X is the XOR of A and Y, and so the output should always be 1. And that's what our truth table analysis would tell us. But if there's a propagation delay, if this has a delay of 5 nanoseconds, and this has a delay of 10 nanoseconds, our truth table is not going to look exactly like this. This might be, nope. I'll catch it someday and let it out. So let's draw a timing diagram for this. So suppose A starts off low and then goes high and then goes low. So Y is the inverse, but it operates with a slight delay. In this case, 5 nanoseconds. And so X, which is the XOR of these two inputs, well, here we have a 0 and a 1, so X is going to be high. Here we have a 1 and a 1, so X will be high. Here we have a 1 and a 0, so X will be high. Here we had another 5 nanosecond delay. And so at this point, we have a 0 and a 0 going into an XOR. And so the XOR is going to output a 0. And it's going to actually take 10 nanoseconds for that to happen. So 10 nanoseconds, we're going to see our output go low. And at this point, our inputs are a 0 and a 1, so the XOR will output a high, and so it'll go back high again after another 5 nanoseconds. I'm not going to ask you to do the timing on these, but I'm putting this in for completeness. But the effect is, right, there's a brief period of time when this truth table is not accurate. There's a brief period of time when A is 1, but Y is also 1. there's a brief period of time when A is 0, but Y is still 0. And so there's going to be a period of time when the XOR is going to see 2 zeros on its input and it'll output a 0. So this is a glitch. And that's a timing diagram, right? Remember, time is going horizontally. So timing diagrams, drawing and analyzing them, knowing what glitches are. Propagation delays, so that's just the time it takes a circuit to respond to changes to its input. And it's generally bigger than 0. Very rare that it's...
Do we have to just talk about adders? Or would we actually have to draw the schematic for one?
You should be able to draw the schematic for one, yeah.
Okay.
So sequential versus combinational, that's basically first half of the course versus second. Combinational is something we can represent with a truth table, other than, propagation delays. To know the value of the output of a combinational circuit, all we need to know is the values of the inputs. A sequential circuit, we need to know the sequence of inputs up to a certain point in order to know what the output is. So that's where we start getting into circuits with memories, which means flip-flops, which means feedback. All right, so yeah, half adder, full adder. You should know what those are, right? The half adder takes in 2 bits and produces a sum and an outgoing carry. And the full adder is almost the same, but it takes in 3 bits. That third bit is called the incoming carry, and it produces a sum and an outgoing carry. So you should absolutely know what these things are. There we go. Right, so half adder takes in 2 bits, produces a sum and a carry. Full adder is like a half adder, but also takes in a third bit, the incoming carry. So definitely know what those are. Write them down on your notes somehow, some form, so that you know exactly what those do. And if you know what the behavior is, you can get everything else from there. So if you have to write the truth table for one of these, right? 2 inputs, 2 outputs. You can write a truth table. 3 inputs, 2 outputs. If you have a truth table, you can write equations. If you have a truth table, you can make a K-map and write minimized equations. And then the way we used these was we put them together to make a larger adder. So if this is a half adder and these others are full adders, you can put pairs of bits A0, B0 through A3, B3. You get some bits coming out.
The schematic a second ago was more about, like, do we draw the internal of the half adders and full adders, like the XOR gates and the...
It depends on the question.
Okay.
So if I asked you to show the design of a 4-bit adder using half adders and full adders, and I didn't want you to draw those, I'll probably say, you don't have to draw the internals of those. You can use the block diagram view. If I want you to actually draw the circuitry for a half adder, I'll say, draw a schematic for a half adder. And that means more than this, right? This is like a system diagram. So in that case, I'd want you to do gates. Same as the midterm, be in Zoom during the exam, right? I'll keep my microphone muted unless I'm saying something. But, if you have a question, go ahead and ask. And if it's a question that is useful for everybody, I'll go ahead and announce it to the whole class. So make sure you're in Zoom and don't hesitate to ask for clarification about something like that. It's a good example.
Will we have to do any wiring diagrams on this?
No, I won't ask you to go down to pin numbers and part numbers, because I think people know how to do that, and that takes a long time. But you will definitely have to get down to, where you're using logic gates. and so on. But I won't make you do particular parts and pins and things like that. Programmable logic. So we talked about the general setup, which was, you know, a AND plane and an OR plane. So this is the way we draw circuits more neatly when we want to represent a sum of products or a product of sums. So you have, for a sum of products, right, you have a section of your diagram that takes care of the ANDing, and then you take the outputs of those and you OR those. That's the sum of products, right? And we can generalize that and sort of make a kind of template of all the different kinds of ways we might want to calculate ANDs, right? And that's called an AND plane. And then we can take the outputs and combine those to feed the inputs of OR gates. That's the OR plane. And so programmable logic at this level is basically looking at which parts of our circuit are configurable, you know, and or both, and then being able to go from equations we want to implement to saying where should we make connections in each of those programmable planes. So those are called fuse maps. So a PAL had a programmable AND plane with a fixed OR plane. A PLA, we could set up both the AND and OR plane, and a PROM had just a programmable OR plane with fixed AND connections. And so you might see a question related to that. All right, other logic blocks. Let me see if there's a good reference for this. So I'm just looking in the book here. So chapter 9 talks about different kinds of logic blocks. So multiplexers, demultiplexers, adders, subtractors. That's not the main ones though. Where do we talk about encoders? Chapter 3. Okay, beyond standard logic. Right, so the 555, definitely know about that. Keep this schematic diagram handy somewhere, and keep these equations handy somewhere. And we've used a 555 a few different ways, or a few different times, but we always use it in this configuration. So encoders and decoders, right, we did those in Verilog. We did those before we got to Verilog. So just more examples of combinational circuits, right, that you can describe with a truth table. This one being useful for, you know, finding the first bit that's asserted in this case. And decoder, good example is a 7-segment display driver, so which I can't imagine asking you anything about because you hook it up and it works, right? And then multiplexers and demultiplexers, which we'll talk about separately. So what do you want to know about a mux and a demux? And again, I mean, you did some of this in the Verilog work also, right? But set of inputs, some kind of selection, and an output. And we use these for routing logic, right? So if we have a series of sources that we might want to choose one to send on to some other piece of your circuitry, you can do that with a selector, right? So this is a 4-to-1 mux. And a demux takes an input and sends it to one of 4 outputs using a select line. Muxers we can also use to generate truth tables, right? We could think of this as 2 inputs and some function of those 2 inputs, and we can just tie these inputs of the multiplexer to logic 1 or 0, and cobble together a truth table for whatever function we want. So that's another use for muxes. Another thing we can do with muxes is use them to build muxes. And so we played around with that a little, where you take like 2 2-to-1s and put them together to make a 4-to-1, and so on. And this is the heart of what goes on inside your CPU typically. It's a lot of steering of data around from one place to another. So you've got a bank of registers, and you've got an arithmetic logic unit, and you've got some kind of memory subsystem, and you've got some sort of I/O subsystem. And how do you execute instructions inside a computer? Well, take this number from the register and take this number from the memory and send them to the ALU and set the ALU up to do an addition, and take the result of that and send it back into this location of memory, and now take this location of memory and that location and send those into the ALU and make it multiply and take the result and put it in this register. And you're just steering data around from one piece of the system to another. All that steering is done with multiplexers and demultiplexers. So this is, if you go down inside the architecture of a CPU, you'll see networks of this stuff. Alright, what else we got? You should know that NANDs and NORs are computationally complete, so we can build any logic gate out of NORs, we can build any logic gate out of NANDs. And those are the only ones. XORs, XNORs don't work. Inverters don't work, but NANDs and NORs will. There's other gates that work, but among those 6 main ones, those are the only ones. K-maps. All right, definitely know how to do K-maps. Like I say, on the state machine synthesis homework, I saw people who were making older mistakes on coming up with K-maps and equations based on those. So what are the things to keep straight? Make sure if you have 4 variables, make sure on the order that you do 0, 0, 0, 1, 1, 1, 1, 0. Don't do it in the usual binary order. Do it in what we call this gray code. Make sure you label somewhere on here what each row or column means in terms of your input variables. When you're doing your exam, I'm going to suggest, if you're figuring out a K-map for J1, call it J1 of A, B, C, D, or whatever the inputs are. Label your K-maps. Just throw something up there, so if I'm checking your work because your final answer was wrong, I can at least see, oh, you did the right K-map, right? Covered it suboptimally or something. And then, from your truth table, if you're doing a sum of products, fill in the 1s on the truth table. If you're doing a product of sums, fill in the 0s. Also fill in the don't cares. If you're doing a sum of products, don't fill in the 0s, just the 1s and don't cares. And you can do that from the truth table by saying, A is 1, B is 1, C is 0, D is 1. So that's 1, 1, 0, 1. Okay, that goes right here, right? Timed test. You can be much more efficient on this if you remember that there's an ordering. If you put your truth table in the usual order, and in this case A, B, C, D. A would be the most significant bit, D would be the least. If you do it in that right order, these will be the following rows in your truth table. Right, but you got to practice this, and you got to know what this means, because there's a dozen ways you can try to do this and end up getting things totally backwards. So practice this, right? But once you've done this a few times, you realize, oh, if I have my truth table and I see all my ones and zeros there, I can just go down and I can just fill them in here, 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 boom, 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 like that. And you just fill in the ones and the don't cares. And then you go ahead and you find your optimal covering. And so make sure you cover the ones. You're allowed to cover the dashes, but you don't have to. You're not allowed to cover any zeros. You can cover ones more than once, and you want large few number of rectangles. Right, so here I would probably cover those, and I would cover those, and I'd be done. Yeah, I could cover this right here, but there's no reason to. Right, I could have more dashes here. I could make a nice 2x2 rectangle here, but I don't need to. And if I do that, I still need to cover this one, and if I'm going to cover this one with a big rectangle, I'm going to pick up this one down here, so there's no reason to use those dashes. They're just there to tempt you. So do your optimal covering and then write equations. And to write equations, you look at all the cells inside the rectangle that you drew, and you see how your different input variables change. If your variable changes, it's a don't care. If your variable is a 0 for a sum of products, it's going to be that variable with a bar on top. If it's a 1, it'll be that variable without a bar. So this block right here, A can change, B has got to be a 1, C has got to be a 0, D has got to be a 1. This block right here, A has got to be a 0, B can change, C is a 1, D is a 0. And again, you notice things when you're doing this. You notice that if you have a 4x4 K-map, every time you have a rectangle with 2 squares, you should get a term with 3 expressions. If you have a single block, you should get a term with 4 expressions. If you have a 2x2 or a 4x1, you should get a term with 2 expressions. If you're lucky enough to have a 4x2 or a 2x4, you got a single expression. Right? Your product term will be just one variable, true or inverted. And if, you know, all of your blocks are covered or none of your blocks are covered, then you just have a constant. So yeah, K-maps are a pain. You might end up doing a bunch of K-maps because you use them for other problems, but go back and just do some practice with K-maps. There's a bunch of examples in the book, and just kind of, you know, dust off those neurons and refine the technique as much as possible. And when you're done, right, if you end up with a nice simple equation, make the truth table for it and see if it matches the original truth table. And, you know, that's your totally solid test that you got a good equation. And, you know, you can just make up problems. You just draw a random truth table, make a K-map, minimize it, take your minimized equation, make the truth table, see if you end up where you started. If you like coding, you can code this. That's a really good way to understand K-maps better. Teach a computer how to do them. I mean, you can teach your friends, but your friends may not want to learn. But trying to explain it at that level definitely helps solidify understanding. All right, K-maps, rules we're going to cover. Oh yeah, don't forget the wraparound. So, you know, if you had a 1 up here, you're allowed to wrap that with the bottom edge and pick up that don't care. You can also wrap from left to right, and if you happen to have, you know, these 4 ones in the corner, you can make this 2x2 box that's unfolded in both dimensions. And if you get a checkerboard, it's a sad day because you know, if your ones are isolated from each other, then all of your coverings are just one by one. And so it typically ends up looking something like this. And you know, each one has got zeros on its neighbor, so you end up with just 8 one by one rectangles. And that's a really, really long expression. But this is actually a K-map for some version of an exclusive OR. And so sometimes, you know, if you see this checkerboard pattern, even in part of your circuit, you can play around with XORs and you may be able to find a quick way to, a simpler way to write that expression. I won't ask you to do that on the exam. I mean, if you see this, it's just an XOR, but I'm not going to expect you or ask you to get tricky with discovering where you can use an XOR. Pretty much sum of product of sums is going to be sufficient. All right, minimization of equations. So, well, via K-maps, we just talked about K-maps, but you can also do some simplification algebraically. We didn't do a whole lot of that, and I'm not going to test you explicitly on it, but, you know, just be aware that you can do algebra. I mean, it's Boolean algebra after all, so, you know, if y equals AB or BC or BE or BD, right? Well, you know, algebraically, I can factor out that B, which tells me if I have, you know, a 4-input OR gate, I can OR that, and then I could AND that with B, and there's my output. And it took me 2 gates. If I just took this and I tried to build a circuit, I need an AND gate, AND gate, AND gate, AND gate, and OR gate. It's going to be 5 gates. And so this is more optimal. Now I got 5 input variables. I don't really want to try to do a K-map with that. And the truth table for this would be 32 rows, and that's kind of a pain. But, you know, if someone says, can you simplify this algebraically, and you start looking at it, depending on your algebra background, right, it's pretty straightforward. I'm not going to ask you to do algebraic simplifications on the exam either, but it's an option. All right, sum of product and product of sum. So now we're getting back to the stuff that I think everybody is pretty comfortable with already. But sum of product of sums, right? So main things to keep track of there. Sum of products. We want to look at the ones. We want to write min terms. And then we want to, you know, take their sum. So if we have a 1 in rows 1, 4, and 5, then our expression will be min term 1 plus min term 4 plus min term 5. Product of sums, we look at the zeros, we write max terms, and then we take their product. For a min term, you can look at the input variables. If the input variable is a 1, we write that variable. If it's a 0, we write that variable with a bar on top. And we AND them together. For product of sums, max terms, it's kind of a dual but opposite process. So we look at the input variables. If the input is a 0, we write that variable. If it's a 1, we write the variable with a bar on top. And then we take their sum. So we OR them together. That gives us a max term. So they're dual processes. If I asked you to write the full sum of product for you know, an expression that you've got a truth table for, you're going to write something like, you know, y equals AB C bar, or A bar B C, or A bar B bar C bar. If I ask you to write it in compact form, then you can write it in something like, you know, y equals. So compact form, you need to put an order on the input variables. So y of a, b, c equals, and you could write something like, you know, min term 6 plus min term 3 plus min term 0. So this is what I usually call a full sum of products expression. This is compact. And the even more compact version would be to say, you know, write a summation symbol, M6, M3, M0. And the even more compact would be just sum 630. And that's like a super duper compact way to write that equation. So sometimes I'll let you write the compact form, sometimes I'll want the full form. Usually I'll say full parentheses, not compact. Okay, so it means actually write out the terms. And then the same thing for product of sums. For product of sums, you know, this is a bunch of things added together, multiplied by a bunch of things added together. And we use the product symbol in uppercase pi instead of a summation symbol. And so it would be a product of max terms. And if you've got this compact form, you see an MD, those are don't cares. So if I did something like plus MD 2, 4, it means that rows 2 and 4 of the truth table have don't care values. And so you can use those in your K-map. All right, let's see, where are we? Theorem proving algebraically and with a truth table. So this is just using truth tables to see when two equations are equivalent to each other. So if I wanted to know, hold on one sec. Nope, that was not the signature required package. If you wanted to know that one equation was the same as another, you can write the truth table for the two equations. And if the truth tables are the same in every row, then you know that the equations are equivalent. The other thing is you can do some algebraic manipulation to turn one equation into another. And that will get you there also. Let's see. System diagrams. Know how to make a system diagram. And this is part of you know, these two items right here. So in general, what's the design process that we keep doing again and again and again? You want to build a circuit to you know, count votes, or control the landing of airplanes, or, you know, a traffic light controller. So you start with a problem that you're trying to solve. You make a system diagram for it. Why? So that you know what the inputs and the outputs are, right? And then you make a truth table. And each input is a column of the truth table, and each output is a column of the truth table. And now you list all combinations of the inputs, and for each combination, you write down in the output columns what the output should be. Now you have a truth table that describes your circuit you're trying to build, and then you write equations, either, you know, a direct sum of products, or using magic, or using a K-map to make minimized equations. And then once you have equations, you can sketch a circuit. So that's the basic circuit synthesis process, right? So this is for combinational circuits, not sequential, not state machines. And the other direction we go in is sometimes analysis. So you're given a circuit and you want to understand it. So make a truth table, right? And so typically you have a circuit. So I don't know, here's A and B gets inverted, and these go into an AND gate, and here's C, and here's uninverted B, and those go into an OR gate, and these go into an AND and an inverter, and there's X, right? So ultimately what we need to do is make a truth table for all these possible combinations. And you can try to do this in your head, but that's kind of error prone. So it's easier perhaps to write an equation for X, and we can do that by making some intermediate values in here. So we could call this C1, and or I don't know, we should call it D and E and F, and then X. And so X is just E ANDed with D, right? So I can start filling in these intermediate values, and then X. And then once I have X in terms of this truth table, I could write an equation for X using, all the stuff we know how to do. So either going from a truth table to an equation to a circuit, or going from a circuit to an equation to a truth table. All right. And now we're getting to kind of the silly part, right? You should know what an AND gate is, you should know what an OR gate is, and so on. Obviously you know these. But right, basic logic gates, just know what they do. If you get confused sometimes, right, put them on your note sheet. And I have seen some cases where particularly in a testing environment, all of a sudden someone will start using this for AND and start using this for OR. And, your answers come out wildly off, right? And you can end up with a 0 on a question because nothing you did looks anything like the answer, right? But if you show enough work, and I can tell, hey, you just switched, AND and OR with each other, and I make that switch and re-look at your problem, and you got everything right, you get most of the credit. So showing your work and speccing it out can help. But if you might do something like this, just put it on your note sheet, AND, period. There's an example of it, A, B next to each other, or A and B, and here's what it looks like. And here's the truth table. Right, and just make one of those for an AND, for an OR, maybe for an XOR, and so on. Spare yourself from having to think more than absolutely necessary, and don't require yourself to memorize anything for the test. On the other hand, don't just use your textbook as your notes, because it's a few hundred pages of lots of stuff, and if you're trying to go through your textbook to figure out what an AND gate is, or what a D flip-flop does, right, that's going to take a lot of time. All right, so know your logic gates. LEDs, I mentioned this the other day. So LEDs, main two things to know is they're directional. So if you're expecting this to light up when you put 5 volts through it, right, this would be where your 5 volts would go. This would be where your 0 volts would go. And don't forget your 1K current limiting resistor. And then we can tie this to ground. So now if this is coming out of some block of logic, right, if you have a logic 1, this will light up. If you have a logic 0, it'll be dark. And then the other side of that is switches, and we talked about this also a few classes ago. If you're trying to drive an input, pull that switch up, pull that input up to 5 volts through a 1K ohm resistor, and then use a switch to optionally connect that input to ground. Switch is open, input is a logic 1. Switch is closed, input will be a logic 0.
That's what you mean by pull-up resistor, right?
That's a pull-up resistor, exactly. And that's something we'll encounter in 270 also, because a lot of the inputs on our devices, we can ask the chip to put a pull-up resistor for us internally inside the chip. And then when we want to connect a switch to a chip, all we got to do is just put this part of the switch in. And this is actually handled inside the silicon. And that's a nice convenience. All right. Gray code and BCD I just put on here as other examples of how we can encode things in binary. So, I won't ask you to count in gray code, but you should know that gray code is a different way that we can count. So normally we count like this, because if we use weighted positional notation and we translate these to numbers, this is 0, 1, 2, 3, 0, 1, 2, 3, 0. But in gray code, we just count in a different sequence. We go 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. And that's the ordering you see on the side of the K-map. Not a coincidence. So that's a gray code. BCD is a different way that we can represent numbers in binary. So if we want to represent the number 15 in binary, it's 4 ones. And this is 1 plus 2 plus 4 plus 8 is 15. But if we wanted to represent 15 in binary coded decimal, we use two 4-bit numbers, one for each digit. So we write 0, 0, 0, 1, that's the number 1, and then we write 0, 1, 0, 1, that's the number 5. And so in binary coded decimal, or BCD, this would represent the number 15. And it's a different number from this, right? 4 ones versus, a 1, 0, 1, 0, 1. But it's a perfectly valid way to represent integers. We can represent integers any way we want. We could, just come up with some random mapping between bit patterns and integers. But, weighted positional notation is a nice way to represent numbers in binary because it lets us do addition and subtraction in the way we're used to. BCD is nice because it lets us easily convert from decimal to binary and back. To convert from 15 to binary, we have to do some tricks and so on. So that's just, the bigger picture here is just that there's different ways we can represent things in binary. Addition and subtraction, pencil and paper, take the carries and ripple them across and so on. We've done this so many different ways at this point in so many different contexts. The book talks about how to detect overflow when you do addition or subtraction in binary. That's not on the exam. We didn't actually get to that, but we'll talk about it in 270, I think. So binary arithmetic, and the big thing to know about subtraction is we can subtract by adding the negative of a number, right, which gets us back into 2's complement. Representing characters in binary, so you don't have to memorize the ASCII table or Unicode or anything like that. But again, just the general theme is we can come up with a mapping between patterns of bits and characters. And we can say, when you see this pattern of bits, that's the letter A, or this is the letter B, or this is the number 7, or the number sign, or the exclamation mark. And, there's no sort of canonical way to do that. It's just, people decide how they're going to do it. And so one way to do that is to use ASCII coding. And it's an effectively random mapping between bit patterns and characters. So that's all that is. Converting between decimal, binary, hex, and octal. All right, so, I'm not going to give you a page of convert these numbers to binary, but I might ask you to convert 1 or 2 numbers. So going from decimal to binary is the trickiest, right? And it's you can do it with trial and error. You can do it by, subtracting powers of 2, or you can do that thing we do where, you take your number, 19 divided by 2 is 9 with a remainder of 1. 9 divided by 2 is 4 with a remainder 1. 4 divided by 2 is 2 with a remainder 0. 2 divided by 2 is 1 with a remainder 0. 1 divided by 2 is 0 with a remainder of 1. And so this is your number in, I do that backwards. Start down here, 1 0 0 1 1. That's your number in binary. So
to do binary subtraction.
So yeah, you should be able to do binary subtraction, but no, I'm not going to ask you to subtract pencil and paper in binary. But I may ask you to do the effect of subtraction by adding a 2's complement of a number. So I asked you to do that on the midterm, so I may not ask that on the final. But yeah, pencil and paper, you should be able to do addition, including adding a 2's complement, but I won't ask you to subtract explicitly. All right, so we can go from decimal to binary. Going from binary to decimal is really just addition and multiplication, right? So this is 1, 2, 4, 8, 16. 16 plus 2 plus 1, that's 19. That's how I get to decimal from binary. And then going to other bases is pretty mechanical. So if I want to go into octal, I'll just break this number up into groups of 3 bits. And this is 5, 3, 5, 7, 2, 7, 4. So this number in binary is this number in octal. And if you want to go into hexadecimal, break it into groups of 4 and write down your hex character corresponding to each group of 4. So 1101 is D, 101 is 5, this is F, this is A, this is 3. And you can always pad with zeros on the left, and so this is 1. And so that's your value in a hexadecimal. And if you start with a hexadecimal number, you can write the binary version by just, writing down 4 bits for each digit. If you start with octal, you can write the binary number by writing down 3 bits for each digit. So octal, binary, hexadecimal, very easy to go from one to the other. You got to know how to translate groups of bits into the right symbol, but it's a mechanical process once you know that. Incidentally, you can also go from, say an octal number directly to decimal, because these are powers of 8s. This is 1, this is 8, this is 64, and so on. And so 5 plus 3 times 8 plus 5 times 64, and so on, will get you back to your decimal number. If you want to go from hexadecimal to decimal, these are powers of 16, 116, 256, and so on. And so you can multiply each of these digits by those powers of 16. Or you can go into binary and add powers of 2. All right, so binary numbers, positive weighted positional notation, negative, we do the 2's complement. To find the 2's complement of a number, toggle all the bits, add 1. All right. Doesn't matter if the number is positive or negative to start. If you want the negative version of a number, toggle all the bits, add 1. So if you're starting with a number and make sure you use the proper number of bits. So if I say we're doing 8-bit 2's complement, you got to use 8 bits. If you want to find what negative 3 is, start with 8 bits. That's positive 3. Right? We know that that's also positive 3, but if we're doing 8-bit 2's complement, I got to have these zeros over here on the left. Because remember, when you do a 2's complement, you're going to toggle each of the bits. And if I don't have these zeros here, I don't realize that when I toggle them, they turn into 1s. So always, know how many bits you're working with and do everything with that full number of bits. So this is positive 3. If I want the 2's complement of that, toggle all the bits, add 1. That's negative 3. If I want the 2's complement of this number, toggle all the bits, add 1. That's the negative of this number, which is positive 3. So 2's complement doesn't mean negative, it doesn't mean positive, right? When you take the 2's complement of x, you get negative x. But x could be positive, could be negative, could be 0. Right? Taking the 2's complement just means find the binary representation for negative x. But there's a nice little trick here, which is when you have a number written in 2's complement, this most significant bit tells you if the number is negative. If this is a 1, your number is negative. If this is a 0, your number is not negative. It's 0 or positive. So 2's complement, signed magnitude is just another way that we can represent negative numbers, which would be, take the positive number and just change this bit to a 1 to make it negative, right? That's not 2's complement. That's putting a minus sign in front of the positive version of the number. We don't usually do that, but there's times when it's useful to do that. Range of numbers, so if you just have, a combination of bits, let's say we have 8 bits, we can represent any number from 0 up to 255. Right, because all ones would be, 1 plus 2 plus 4 plus 8 up to 128, that's 255. All zeros is zeros. If we have 2's complement, we can go from negative 128 to positive 127. So it kind of shifts your range. But in general, the more bits you have, the more numbers you can represent. Importance of using n bits, so, if you're doing 8-bit 2's complement, make everything 8 bits, even if you only need a few bits to represent it. And then the beginning of the course was just this whole idea of digital versus analog. So, analog is sort of continuously changing values, the kinds of voltages we see in ECS 120 were analog values. Digital, we sort of break things into these discrete pieces. So if we have a single bit, it's either a 0 or a 1. If we have a circuit with a single output, it's either 0 volts or 5 volts. And if it's 4.8 volts, we just call it 5 volts. We say that's a logic 1. Right? And so there's degrees between that. We can move towards an analog, and so this is what we do sometimes when we convert from analog to digital. We use bits. I didn't list analog digital converters on here. I won't ask you anything about digital analog converters. We'll get to those in 270 in more detail, but those questions on resolution and number of bits, I won't ask you anything about that. All right, we are 42 seconds past time, but anyway, that was a wordy rehash of all of Engineering 250. So I have office hours tomorrow morning. Those are my last office hours for the year until summer. So any lingering questions, come to office hours tomorrow. Otherwise, I will see you on Tuesday on Zoom. Hopefully, exam will open up at 12 on Canvas, and I'll be in the Zoom classroom if there's any need for questions or clarifications. Otherwise, have a good weekend. Good luck with any exams you have before then, and I will see you next time.
Thank you.
All right, and thank you everybody for your hard work this quarter. It's been a really good class for me.
Thank you.
Thank you.
Thank you.
Have a great weekend.
Thanks, you too.
See you summertime.
All right, definitely.